Hi, ladies and gentlemen. Welcome to lesson 26. So we are post spring break, and what we have are 15 lessons left for the remainder of the course. We have several new items that we're going to discuss, and really the point of the first part of this course has been directed towards what we're about to do, which is a heavy emphasis on applications, but we need to make sure that we understand how all of the information that we're going to talk about fits into the context of everything that we have covered thus far. So, what we've been doing really is building the foundation, and now we are going to build up on that foundation and start digging into some serious applications. Let me just show you the overview here for post spring break. So, we have 4 things left to do in the course in our 15 lessons. We have chapter 6, which is Eigenvalues and Eigenvectors, otherwise known as Eigenstuff. Chapter 7 is singular value decomposition and principal component analysis. This is really where we're going to leverage the information that we cover in section 6.3 in order to jump into some of the serious applications. Chapter 8, we're going to revisit the idea of matrix vector multiplication as linear transformations. This is where Strang covers it in his text. We've already seen a lot of this, so we're just going to build on some of what we know and provide a little bit of new information. And then finally, we're going to finish up with another application, which are the Markov matrices. So let's jump into chapter 6 here. This is the overview. Make sure that you take a look through and read the entire overview. There's a lot of good information in here with respect to what it is that we're going to be doing. And we'll talk today about the definition of eigenvalues and eigenvectors, and we'll provide the entire concept and structure of what this is, along with how we do the computation to calculate these. We're also going to talk about diagonalizing a matrix. That's going to be lesson 27. And then finally, we'll talk about symmetric positive definite matrices, and that's lesson 28. We will not be discussing the complex numbers as they relate to vectors and matrices. In other words, we're not going to talk about matrices where the entries of the matrix itself are complex numbers. Also, we're not going to do section 6.5, which is solving systems of differential equation. If you want a course on differential equations, we have one, and it's a good thing to know, but in general, lost the machine there. It's a good thing to know. However, it's not something that we're covering in this course. So if you want to take that and build your knowledge base, that's great. Not something we're going to do here. So let me just emphasize a couple of things out of the introduction. Again, you're going to read through this here. It's quite short, but he provides an overview of what it is that we're doing. First things first, all of the conversations for eigenvalues and eigenvectors relate to square matrices. It's just like the determinant conversation. It's just like the inverse conversation. It only applies to square matrices. And then we'll take a look at what the eigenvalues and eigenvectors are. And that's what we're going to do right now. We'll just jump right into section 6.1. A little bit about the overview, and then we'll get into the nuts and bolts. So again, this is the definition, and we will talk at length about what it means and how we do the calculations. The second item that he lists here is really an application, and when we will emphasize that more in section 6.2. This is where we are going to repeatedly apply the linear transformation. Remember, a times x is the same thing as the linear transformation of applying a to the vector x. This is where the whole picture of the 4 fundamental subspaces comes from. We are mapping Rn to Rm. We're mapping into the column space of A. And we've discussed this repeatedly, and we're just coming back to this again, and we'll talk about it some more when we look at what the eigenvalues and eigenvectors really are. Also, then we have in here the conversation about determinant. So the determinant, right, we're going to take a look at when the determinant of A minus lambda I is 0, and we'll talk about that. That's all part of how we do the calculations. Another determinant conversation, it turns out a couple of important items here. This is the more important of the 2 items. The product of the eigenvalues is equal to the determinant of the matrix. And we'll write that down again, but that's a very important idea. Product of the eigenvalues is equal to the determinant of the matrix. Remember, we only talk about square matrices. And then the sum of the eigenvalues is equal to the sum of the diagonal elements. This is also called the trace. So the trace of A is equal to the sum of the elements that are on the diagonal in the matrix A. And it turns out that that sum is equal to the sum of the eigenvalues, interestingly enough. All right, let's jump right in then with what Strang's talking about. This chapter enters a new part of linear algebra, so definitely agree with that. He says that we have been spending a lot of our time solving AX equals B, and we certainly did do a lot of solving AX equals B. However, we also laid the foundation for what linear algebra is all about, and now we're going to use that information as we move forward. He makes a claim here, and let me just circle this. He makes the claim that the second part of his book is about change. So that's true. However, there are some of the applications, for example, the differential equations, which is really about change. Derivatives are rates of change, and so differential equations are all about rates of change and change itself. And we aren't covering that information. So it is about change, but not necessarily in the way that we would think about it. So let's jump right into eigenvalues and eigenvectors. And so he makes this claim in bold: we want eigenvectors that don't change direction when you multiply by A. Let's expand on what that actually is. It isn't so much changing direction, it's about being in an invariant subspace. So first things first, the word eigen is a German word. The proper writing of all of these terms here, let me give you an example. Anytime we write eigen anything, it should be capitalized. It's a German word. And that noun is something that would be capitalized. So a lot of modern textbooks don't do that. No big deal. Just to let you know. What the word means is it means own. And this is not the verb to own. This is as in essence. And that's what eigenvalues and eigenvectors are all about. They are the matrices' own vectors and values. They are what make the linear transformation into what the linear transformation actually is. It's the essence of the linear transformation. That's what we're talking about. And we can see that in the definition. Let's go back for a second. So he talks about it right here, but AX equals lambda X, where lambda is a complex number, right? So we can have complex eigenvalues. And we'll talk about that. I'm going to give you an example in just a minute of what this is. So what we are looking for, if we think about this as the linear transformation, we are looking for vectors that when they get mapped by A, end up staying in the same subspace. They end up staying in their span. Because what we're going to get out of this is just a scalar multiple of the same vector. That's what eigenvalues and eigenvectors are. Eigenvectors are the directions of invariant subspaces. The subspaces that exist where when I apply A, I stay in the same one-dimensional subspace. They can be two-dimensional. I'll show you an example, I think, next time where we talk about two-dimensional subspaces. But this is what the concept of eigenvectors is all about. And eigenvalues is just a scaling. It's a scaling in that particular direction. He talks through this information, and we're going to use his Markov example, which he uses regularly throughout this section. We'll talk about Markov matrices at the end of the course. That's okay. The examples are wonderful. Let me give you an example of what it is we're talking about when we talk about invariant subspace. Here I have a matrix A, and what I'm going to do is I'm going to use the map program. The map program is available to you. I've put it in the files for the course, and this is the matrix we're talking about. -3, -5, 2, 4. That's our matrix. And what we want to do is we want to take a look at what happens when we map a vector using this matrix. So we're going to start out with the vector 4, -2, and I'm going to hit the map command. And when I do that, and it's a little hard to see here, it came out yellow. Let me clear and try again. So remember, so I've scaled the axes from 8 to 8. It starts out as 2 and 2, but you can come in here and you can change the axis limit. Remember, I can enter in a value for my vector. So I'm going to go with -4, 2. And we end up with the yellow vector. Let me do it again. So we end up with a better color. -4, 2. No, we get the same one. Map. Now let me try it again. -4, 2. I should go into the map program and change and remove that color. The color's hard to see. So here is our vector. When we map it, it comes over here to the blue vector. So that's a times x. Now what we're going to do is apply a again. So this is the new input, and we map again, and we get the orange vector. That's our new input. We're going to map again. We get the purple vector, and we continue on, and now we have this kind of yellow vector. That now is the input, the green vector, etc. We're continually applying the matrix A. So what happens, instead of -4, 2, let me clear this. What happens if I put in the vector -5, 2? -5, 2, that gives me this green vector, and when I map it, I get the blue vector. And you notice it lies along the same line. If I think about the one-dimensional subspace that exists along this vector, I've stayed in that subspace. And then I do it again, and I map again and again and again and again. And you can see that we have in -5, 2 an eigenvector. This is a vector that is staying in the same one-dimensional subspace. Not only that, we can tell what the eigenvalue is. The eigenvalue here is -1. Every time we put a vector in, we end up with -1 times that vector out. This is the whole concept of eigenvalues and eigenvectors. Let me show you another one. I'm going to put in the vector -1, 1. So we have -1, 1, which is this vector right here. And now when we map it, we have the vector -2, 2. And we map again, -4, 4. Map again, -8, 8. What's happening? We're staying in the same subspace. So the vector hasn't moved off of the subspace defined as the span of the vector -1, 1. And every time we apply A, then the length of that vector increases by 2, which means the eigenvalue is equal to 2. Again, this is the entire concept of what it is we're talking about. So when we have the vector -4, 2, let me put it in one more time. So we have the vector -4, 2. This is actually a linear combination of the two eigenvectors. And the portion that's in the direction -5, 2 is going to get flipped around. It's just being multiplied by -1 every time. And the piece of this vector that's in the direction 1, 1 gets doubled every time. So when we map this the first time, a lot of that vector is pointing in the -5, 2 direction, and it gets flipped around. And then we map this vector, which is again decomposed into a sum of the two eigenvectors. And when we map that, part of it gets flipped around and part of it gets doubled. And as we continue on, we can see the flipping and the doubling as we proceed. And that's what's happening as we continue to move forward. And you'll notice what do we start to do as we continue to apply A many times, the doubling portion is taking over. It's making the output vector larger and larger in magnitude. The flipping back and forth is still happening, but that's only happening of the same dimension as the very first vector. So we end up with something that's almost in the direction of the second eigenvector. This is the whole idea of eigenvalues and eigenvectors. All right, I'm going to clear this out and put that away for a minute. So this is just an example of what we have. Let's take a look at example 1. In example 1, Strain gives us the following matrix. And this is a Markov matrix, which again we'll discuss later in the course. But he tells us that we have eigenvalues lambda 1 is equal to 1, and lambda 2 is equal to 1/2. And then he gives us the associated directions. Now, one thing to note, he uses x for eigenvectors. Most textbooks, most references will not use x as the eigenvector. They'll use v, or they'll use k, or they'll use some other letter to indicate an eigenvector. But Strang just uses x, so we'll continue on with what he does. So then he tells us that the eigenvectors associated with these eigenvalues are equal to 0.6.4 and 1, negative 1. So the second eigenvector is 1, negative 1. And now let's stop and think for a minute. If we have any vector z in R2, I will be able to write z as a linear combination of the two eigenvectors. And as we just saw, what's going to happen when we apply A to the vector z? Well, we're going to end up with c1ax1 plus c2ax2, and we already can see what's going to happen. What is A times x1? It is the eigenvalue times x1. So this is going to be, the eigenvalue associated here is 1. So this is going to be c1 times 1 times x1 plus c2, and then A times x2, here's the other eigenvalue, is going to be 1/2 times x2. So every time that we apply our matrix A, we are going to end up keeping the direction of the vector that we started with, that's pointing along 0.6.4, and we're going to shrink the part of the vector that's pointing in the direction 1, negative 1. Let's do this again in the map program. Let me pull it up. All right, so I've brought up and entered the matrix here. We have the graphic, and I've rescaled to 1.5. And what I want to do is I want to use the unit square. So remember, the unit square represents an infinite number of vectors. It's all the vectors that point to somewhere inside of the unit square. It's all those linear combinations. And what do we expect? We expect for each of those vectors for us to maintain the direction 0.6.4 and in the direction 1, negative 1 to be cut in half. So let's map this. So we can see along the 1, negative 1 direction, we have been cut in half, and then this is maintaining the direction of 0.6.4. Let's map again. Map again, map again. So we continue this mapping, and what we see is that the portion of all the vectors that was in the direction 1, negative 1 has been shrunk down towards 0. And we're left only with the resulting portion of the vectors that points in the direction 0.6.4, which is the direction 3, 2. If we were to draw the vector 3, 2, we would see that it would line up right along with what we have here. Again, this is the idea of eigenvalues and eigenvectors. A hallmark of Markov matrices is Markov matrices always have one eigenvalue equal to 1 and all the other eigenvalues with magnitude less than 1. So with repeated applications of a Markov matrix, we will shrink down everything that is not pointing in the direction of the eigenvector associated with the eigenvalue of 1. So he talks about exactly what we just discussed here. You can read through this material. He has the same conversation about the impact of the eigenvalues and eigenvectors. I just wanted to show you, and remember, you have access to the map program, so you can go and explore these things for yourself. We still have another example or two that's coming up. So example number 2 here is the projection matrix. So I've written the matrix down here, and he goes on to tell us, hey, we have 2 eigenvalues. One of the eigenvalues is 1, and one of the eigenvalues is equal to 0. And for this particular matrix, we have the eigenvectors. So the eigenvectors for 1, he tells us, is 1, 1. And the eigenvector for 0 is 1, negative 1. As we discussed before, every vector in R2 can be written as a linear combination of these vectors. And now let's think about what's going to happen when we apply P to Z. What happens when we apply a projection matrix to a vector? Well, we project it onto whatever column space was used to create the projection matrix. In this case, it's a one-dimensional column space. It's a one-dimensional space that was used to produce this. Let's think about it in terms of eigenvalues and eigenvectors. We're going to end up with C1px1 plus C2px2. And what's going to end up happening, we're going to have, again, P times x1 is the same as lambda 1 times x1. And lambda 1 is just 1. So we're going to end up with C1x1 plus, and now we have C2 times, what's P times x2? The eigenvalue is 0. This whole piece gets mapped to 0. This is the projection. We knew this was going to happen. Whatever the vector is, we are going to project onto the 1, 1 vector. We are projecting onto the eigenvector that is associated with the eigenvalue of 1. It's exactly the same as we discussed previously with projection matrices. We are projecting onto that subspace that is associated with the eigenvalue of 1. And we can see that just through the arithmetic part. He goes on and talks about it here. You should read through. He talks about the projection piece of this. I just want to relate, and this is an excellent example on his part, I want to relate the projection matrix to the eigenvalues and eigenvectors because we can see very clearly why we're going to end up with just the piece that is in the direction of the eigenvalue that has size 1. All right, so how do we actually calculate the eigenvalues and eigenvectors? That's what we're going to do. We use this equation here, and let me talk about where that comes from. So we're going to walk through an example. Of course, MATLAB will find eigenvalues and eigenvectors for us, but there's some value in us practicing with these 2x2 examples to help us build our intuition as to what's actually happening. First things first, we're going to start with the definition. Ax equals lambda x, and we know what this means. We are looking for x vectors that are in invariant subspaces, such that when they get mapped by A, they are just scalar multiples of themselves. Whatever that subspace is, we want to find it so that we know where these eigenvectors are located. Let's do a little bit of, we have a vector here, ax. I'm going to subtract lambda x off both sides, and that's going to give us the 0 vector. Now what I want to do is I want to factor out an x, but I can't just write down a minus lambda times x equals 0. That's not going to work because A is an n by n matrix. Remember, always square. Lambda is a scalar. So how do I turn lambda from being a scalar into an n by n matrix? I multiply by 1. And 1 is multiplying by the n by n identity matrix. Now we have this equation here. This is what we want to solve. And we're looking for solutions. X equals what? We want these invariant subspaces. Well, immediately you know one solution, x equals 0. Okay? X equals 0 is never an eigenvector. This is never an eigenvector, and I will abbreviate eigenvector as capital E vec. We know x equals 0 solves this. X equals 0 is not a subspace of interest to us. We are never interested in that solution. So we're looking for non-zero solutions. Let's go back for a minute. How are we going to solve this equation for x vectors that are non-zero? Well, you know from the first part of the course that in order for this to have, what we're really asking for is, I want the null space of A minus lambda I to be non-trivial. I want it to have something of dimension 1 or larger. So how can that be possible? So this has dimension 1 or larger if A minus lambda I is singular. Okay. What's true when a minus lambda I is singular? The determinant of a minus lambda I must be equal to 0. That's one of the properties when A is a singular matrix. In this case, of course, it's A minus lambda I. We're looking at the whole matrix that results from A minus lambda I. And that's where he comes up with this equation. We want the determinant of A minus lambda I to be equal to 0. So step 1 in the process of finding eigenvalues is right here. We solve for the lambdas. We find what lambdas make A minus lambda I singular. Okay? Step 2 then is to take those eigenvalues and plug them back into A minus lambda I times x equals 0. And when we do this, now what we're going to be able to do is we're going to be able to find the eigenvectors. So we start by finding eigenvalues, and then we use those eigenvalues to solve for the eigenvectors. This is the process. What we're going to do is we're going to walk through this process given this matrix here. So let me just copy this out and move it down over here. And we're going to just walk through exactly how this works for practice purposes. All right, step 1, determinant A minus lambda I has to be equal to 0. So let's take a look at what this is. What is A minus lambda I? That's equal to, I don't need a parentheses there, A minus lambda I is equal to -3, -5, 2, 4, minus the identity matrix, which is 1, 0, 0, 1. So we want the determinant of -4, this is times lambda, right? So it's lambda times I. So we want -3, not just a 1, -3 minus lambda, and then we want -5, and we want 2, and we want 4 minus lambda. So we want this determinant equal to 0, and that determinant is equal to -3 minus lambda, and then 4 minus lambda, minus a -10, so that's plus 10. And now we just do a little bit of expansion here. We have lambda squared, and then we have -4 lambda plus 3 lambda is going to give us negative lambda, and then we have -12 plus 10 minus 2 is equal to 0. This is something that's easy enough for us to factor. We can see that we have lambda -2 and lambda plus 1. And then we know right off the bat, we know lambda is equal to -1 and 2. Those are the two solutions to this quadratic polynomial. So one thing to note, one of the advantages of doing a few of these by hand, the process is always going to yield a polynomial in lambda. And so we're going to be able to solve it. We're going to be able to find roots to this polynomial. That's what we're solving for. And in this case, we have lambda equals -1 and lambda equals 2. Now what we're going to do is we're going to solve A minus lambda I times x equals 0. By convention, we end up just numbering. It doesn't matter which order. Oftentimes we go smallest to largest, but it doesn't make any difference. We're going to end up numbering the eigenvalues. So we're going to say the first eigenvalue is -1. And what that gives us for A minus lambda I, we have our A matrix. So we have the A matrix up here. And now we're going to subtract -1 off the diagonals. So we have -3, -5, 2, 4, and we're going to subtract -1, 0, 0, -1, and the result of that is going to be -2, -5, 2, 5. Let's take a look at this matrix for a minute. What's true about this matrix? It's singular. Of course it's singular. We picked the lambda values to make it singular. That's the entire point of the eigenvalues. So because this matrix A minus lambda I is singular, we know it has a non-trivial null space. And what we want to find then is, we want to take -2, -5, 2, 5, and we want to multiply times an eigenvector to get 0. And we can see very easily an eigenvector that works would be something like -5, 2. And when we were doing the map program, that's exactly the vector that we put in that gave us a -1 eigenvalue. So we have one eigenvalue eigenvector pair. And that's this grouping right here. So for the next one, we have lambda 2 is equal to 2. We end up with -3 minus 5, 2, 4, minus, and we're going to subtract 2 times the identity matrix, which is going to give us a -5, -5, 2, 2. Again, we can easily recognize this is a singular matrix. And what we want to do is we want to find out what the null space is. So we have -5, -5, 2, 2, multiplied times some vector equals 0. Again, it's very easy to see what this vector is. x2 is equal to -1, 1. And pairing that up then with the second eigenvalue, we have our second eigenvalue eigenvector grouping. Now, some of you are going to say, hey, wait a minute, I could have picked one -1. That's exactly right. The eigenvectors lie along an invariant subspace. Any vector along that invariant subspace will work. They're all eigenvectors. We are only going to pick one of them, of course, but we can pick any one we want. Most software will take this and will turn it into a unit vector. Most software, like if you did this in MATLAB, it would give you x2 is equal to 1 over the square root of 2 minus 1 over the square root of 2. Because that is the same eigenvector. It lies along the same invariant subspace. So this is how we do the calculations. You're going to have to do some of these for the homework, and you'll be responsible to be able to do just the 2x2s, not even the 3x3s, just the 2x2s. You'll be responsible for those when we have quizzes and tests. So Strang's version of what we just discussed with the two-step process is right here. We're going to compute the determinant of A minus lambda I, and we're going to find the eigenvalues. And then taking the eigenvalues, we are going to figure out what the eigenvectors are by solving for the null space vectors for whatever A minus lambda I we happen to have. Okay, let's talk a little bit about the determinant of trace, and we'll talk about triangular matrices. So big result is the determinant of the matrix A is equal to the product. So the capital pi symbol is similar to a capital sigma, except instead of adding things up, we take the product. It is the product I going from 1 to n of the lambda i's. So the determinant is the product of all the eigenvalues. Just like the trace of A is equal to the sum I going from 1 to n of all of the eigenvalues. We can go back and take a look at this in the previous example. So the eigenvalues we found were -1 and 2. We add those together and we get 1. If we add the trace, and let me circle the trace for you, the trace is the sum of the diagonal elements. If we add together the diagonal elements, we can see we have 1. That's always going to be true. We can also tell the determinant of this matrix. The determinant of the matrix is the product of these two things, which is -2. And if I take the product here, I have -12 plus 10, which is -2. So the eigenvalues actually give us, through these two equations, some useful information about the matrix itself. What we want to do now is specifically take a look at triangular matrices. Two things about the triangular matrices, and let me move this matrix over here. So the triangular matrix, you know that we can find the determinant very easily. The determinant for this matrix is equal to 35 times -2, which is -70. We just took the product of the values along the main diagonal. It turns out, in any triangular matrix, the eigenvalues are the values along the main diagonal. And this is actually pretty easy to see. I just want to show you quickly why this is true. A minus lambda I we're going to take this determinant, we're going to set that equal to 0. Let me just write out what this would be. Negative 2 minus lambda, 3, negative 4, 0, 5 minus lambda, negative 6, and then 0, 0, 7 minus lambda. And we want the determinant of this. So the determinant is equal to, well, the determinant of this matrix is the product of the elements along the diagonal. So the determinant of this matrix is just negative 2 minus lambda, 5 minus lambda, 7 minus lambda. And that's equal to 0. And what do we see? We already have factored the polynomial that gives us the eigenvalues. The answers are whatever the elements were on the diagonal. So triangular matrices have a lot of advantages, and one of the most important is the fact that we can just pull the eigenvalues off of this matrix directly. Let's talk about imaginary eigenvalues and what this actually means. Great conversation here you want to read through. He talks about rotation matrices. What I'm going to do instead is I'm going to look at a different example, this one here, and we're going to walk through the process again of finding the eigenvalues and the eigenvectors. So step 1, and now it'll be a little bit quicker, I want the determinant of a minus lambda I. So I want the determinant of minus 3 minus lambda, 8 minus 1, 1 minus lambda. I want the determinant of this matrix, and I want to set that equal to 0. So that's a negative 3 minus lambda times 1 minus lambda plus 8 is equal to 0, and that's equal to, I have a lambda squared, and then plus 3 minus 1, so plus 2 lambda, and then a minus 3, so that's plus 5. This is going to require the quadratic the quadratic formula, or I could complete the square here. Completing the square is actually probably the easier way to go, so let me do that. 0 is equal to, I'm going to end up with lambda plus 1 quantity squared, and then I've added 1 to the outside, so then this is going to be plus 4. So the lambda values are equal to, I'm going to take negative 4, I'm going to take the square root of negative 4, and then I'm going to subtract off 1. So the lambda values are equal to negative 1 plus or minus 2 times I. Those are the eigenvalues. The eigenvalues in this case are complex. And what does this mean when we find the eigenvectors? The eigenvectors are complex. I'm not going to go through that example, but it's easy to verify and easy actually to find in a 2x2 case what those eigenvectors are going to be. What does this mean in the map program? What does it mean when we have complex eigenvalues and eigenvectors for some matrix? Let's take a look. All right, so I have the map program up here. This is the matrix that we're interested in. And I'm going to use a different icon this time. I'm just going to draw a mouse vector. And sorry, we're back to the yellow vector here. But the question is, what's going to happen? Well, when we map, we can see we rotated to the right, and we rotated, and we rotated. We keep rotating around. There is no invariant subspace, not in real numbers. If I continue mapping, we're going to continue rotating around. So this is just our demonstration, and let me change the axes limits. Let me go out to 10. Right? And we can see that we have the vectors actually continuing to grow. So we map around, and there is no place where we're going to have an invariant direction. We just rotate. Well, did we know that was going to happen? And the answer is sure. We knew that was going to happen because what we have is, remembering Euler's identity, if we have an e to the I theta, that's equal to cosine theta plus I sine theta. And whenever we have a complex eigenvalue, we're going to end up with rotations. So he talks here about the rotation matrix. This is where we have a purely imaginary situation. And that gives us just a rotation. Whereas in the case of the exponential that has a real part, then we're going to get some growth or decay associated with the eigenvalues when we look at mapping the eigenvectors. And that's what we see. So we get this rotation. There are no invariant subspaces. And then the vectors can grow or shrink based upon the components of what we have for our eigenvalues. All right, that leaves us with the last topic, which we're leaving you to read here. This is the eigenvalues of the product and the sum. And he's just making a point here, read through this, that there's not necessarily a lot that we can tell based upon the eigenvalues of A and B independently. He does give an interesting result here. We'll leave you to read that. And then, of course, he does a nice job of reviewing the main ideas. So kind of, in the Air Force style, tell them what you're going to tell them, and tell them what you told them. And so he's reviewing what he told us associated with eigenvalues and eigenvectors. And then he's got some excellent worked examples here. Recommend that you go through all of these to be able to help build your understanding of eigenvalues and eigenvectors. For today's question, here's today's questions. Right, list all the things we know about the matrix A when A has a zero eigenvalue. We talked about that. Talked about eigenvalues and determinants, talked about eigenvalues and complex numbers. And then this is a chance for you to practice by hand finding eigenvalues and eigenvectors. That's it. We look forward to seeing you in class. Thanks.